Really, thanks a lot to Brad for coming and allowing us to have this this opportunity to share our work and talk about what I think is a great area of high dimensional inference. And I'm also thankful that somebody put my slide up early, because I worked a long time on that title, and it's got a lot of mysterious words in it that I'm going to tell you all about. And also quickly will acknowledge my student, Drew, and Ann Lee, who is the one who did all the hard stuff. So let me tell you what that mysterious title is about. And so I'm going to be talking about a genetic problem. And when I first met Brad, I was an assistant professor, and I was just about to give a talk, and my talk was on genetics. And Brad said, well, genetics talks always cause my eyes to glaze over. So I thought, well, I'm really ready now. I'm feeling confident. But isn't it terrible the way people remember those things? But I will give what I hope is a fairly simple background to the genetics, and it is really very simple. And then talk about how we can use this modern dimension reduction method of TREELETs to learn a lot, and really all these things relate back to the early days of Stein and Efron and all the people that we admire for how to learn in surprising ways from data that's seemingly unrelated. And so I want to tell you about that, and I'll put it all in the context of heritability. So in the end, my final part will be about the heritability of body mass, which is, I notice, being talked about a lot these days. So our goal then, is to estimate how related people are. And of course, you know who your brothers and sisters are and stuff, but there's probably somebody in here, well, maybe not anymore, but it could be somebody here who's my 7th, 8th, or 9th cousin, and certainly I wouldn't know that. And so that's the kind of distant relatedness that I'm interested in, is estimating that kind of thing. And so the kind of data that I have is SNPs, but I promise you I won't talk about GWAS. So it is GWAS data, but we're going to use it in a different way. And so just in case you don't know what a SNP is, it is a position on the genome where some of the people will have a C there, say, and some of them will have a T. And so the genotypes can be coded as 0, 1, 2 based on how many copies of C that they have. And so you get a big matrix that's N by however many SNPs you have, maybe 500,000. So you have a lot of information about people. Each bit is not very informative, but altogether you can learn a lot about people and how related they are. And one of the things that's extremely neat about the genome is if you're my 5th cousin, then we have the same correlation all across the genome. So if I look at the correlation of any of our SNPs, it should be this A parameter, Aij, is going to be how correlated somebody is with somebody else. And that's going to be the same all across the genome. So you can learn so much about people. And that's how they figure out different correlations, like they make those pretty plots that finds the different ethnicities. That's all based on that fact of the genome having this common information across it. And this project is just used to motivate it. I'm not going to get any findings about Palau today, but Palau is a small island in the South Pacific, and it began like with a group of people who came on a canoe, it's believed, and then their population built up, and then the Europeans came in, and most of them died, and so there were very, very few people there like 140 years ago, and now the population is built up. So it's kind of neat because it's not neat that everybody died, but it's neat that they're all related to each other. And so this is a great place for trying to map a disease if everybody's related. It's one big, big, big pedigree. And so, well, so we know everyone's related, and they do collect some information in their pedigrees, but it's not really very accurate, because if they adopted somebody, they still call that a family member, but for genetic studies, they're not. And of course, they're related. There's, you know, relationships that are never recorded. And so all of that makes it hard to know how related the people are. But since everybody's related, we thought that the matrix of pairwise relatedness would be, we could use that to get the to improve the individual pairwise related. You know, all the relationships between everybody should help you to get the specific relationships between pairs. So it seemed to motivate using some kind of high-dimensional stuff. And so the first thing I tried was PCA, and it failed terribly, because relatedness is a very local phenomenon, and we need to know about relatedness I mean, PCA is a global method, so we need to try something different. But now I'm going to give the little bit of background of genetics. So this thing I want, AIJ, it means basically what proportion of your genes do you have from the same ancestry as somebody else. So for identical twins, it's all of them. For a parent-child, it's half of them. If you're first cousins, it's an eighth of them, and it drops down very quickly. So one way of people in common talk, they talk about degrees of relatedness, and that's just minus log 2 of their AIJ. And AIJ is the fraction that they share. So for instance, this father and his daughter share half, and likewise these two daughters share half of their DNA is from the same ancestor. And those were first degree related. And second degree related are, you know, grandfather and granddaughter. They share a quarter because there are 2 steps, and so forth. And you can see how it very, very quickly gets down to 0. And so fifth cousins are just barely related, and yet it's still got information in it. And so at any rate, you can't just look at their genes, because we're all, you know, there's not that much, you know, we all have things that are what are called identical by state, meaning that, say, in many, many places, say, even Brad and I will be the same, right? Even though it won't be in the IQ ones. So we can't just look and see if they match. We have to see if they came from a common ancestor. And so if we had all of the pedigree, we could work this out using a recursion. But of course, we don't have that. And so we just look to see how often do they match, and then we look at the allele frequency, and we use an MLE to get that. But it's not perfect. It's very noisy, and in particular, the ones that are close to 0 can't be differentiated from the ones that really are 0. And so we decided, and Ann Lee is my colleague, and she published this paper. It was one of the early papers that was published in the Annals of Applied Statistics. I think Brad asked her to submit this. And it's a very neat paper, and let me try not to do too much harm by describing it. And what this method does is it creates a basis for data that is built by looking to see each variable. You look to see which variables are the closest together, and then you do the pairwise PCA there. And you keep moving up the tree, so you find the variables that are closest together, you merge them, you keep doing these projections, and you get the main axis and then the difference. And you move up, and you get a whole basis that way. And the basis is built by clustering the variables that are closest together. And then it builds up the orthonormal basis. And in our case, these nodes would be the people. And so the people are naturally going to cluster by how genetically similar they are. But to give you a feeling, just a feeling of how this is different than PCA, if you took the data that Anne has here and did PCA, each row here is one of the basis vectors. And you can see how smeary it is. Gray is 0, black is -1, and white is +1. And then you can see when she uses treelets how it gets these clean black and whites that pick up the local structure that's in these data. And so that's what's so neat about treelets, and that's why we thought this was a perfect application of it. And when she wrote her paper, she wrote about having a vector of variables and how you would express it using this basis that you had constructed. But we don't actually ever observe X. All we ever observe is we're going to have an estimate of the correlation of X. So think of X is like some, in animal science, they actually call it, if you were looking at some important quality, they call it the breeding value. So it's your genes at whatever you're interested in. So we don't observe the genes for what we're interested in. We just observe how correlated all the genes are. That's what our data are. Remember, I kind of rushed through it, but we estimated how correlated everybody was by looking to see how often they shared common SNPs. And so we express this correlation using the, just writing it in terms of this basis. And you get, here you get the diagonal pieces, the variances, and here you get the off-diagonal pieces. And this is just another way of expressing our noisy data. So we have A hat. We don't have A. We have a messy A. And we want to kind of use this decomposition to somehow clean it up. So we want to get many, many, many people are not related. So we want to find the zeros, basically. So what we do is we hard threshold the coefficients. The coefficients come from the variance and covariances of these, and we want to throw out any that are close to 0. So we hard threshold by lambda, and that gives us a cleaned up A, and let's see whether it works. So first I'll show you a simulation. We simulated data like Plow. So we simulated people for 8 generations of random mating, and then we have a big pedigree, and we look to see if we can rediscover the pedigree using treelets, which would be kind of remarkable. And in fact, it does work. So here's a piece of the big pedigree, the red people. So this is like mother, father, these are their 3 children, and so forth. This is mother, father, their child. And so all the red people are the people that treelets found and clustered together in this part of the tree. And you can see they really are related to each other. And so treelets is more or less recapitulating this pedigree, and all we gave it was pairwise correlation. So it's kind of remarkable. Now we thought, well, let's push it even further. So we're going to generate a ridiculously uninformative data. We're going to generate 1,000 pairs of people. They're unrelated to one another, but each pair is 5th degree relatives. That's third cousins, basically people you don't know. Okay, so we've got pairs of third cousins, and we're going to try to recover A using treelets. We'll first get A hat. Now realize that the whole matrix is zeros except these 2 by 2 blocks, and the off diagonals are 0.03, so they're near 0. So on the left, this is so sparse you can't really see it very well, but on the left you see there's the noisy data. Down the diagonal you should see some structure, but you see nothing. That's what went into the program. Then I don't know if you can really see it, but if you could, you'd see that right down the diagonal it found those pairs, and those are whiter, but it doesn't show very well. So you can see this shows the error, so the error before in the matrix and the error after, almost all 0. So it seemed a miracle to me that there was the only 2 people who related to each other, somehow they learned from all the people who were completely unrelated. It was a miracle. So then we thought, well, now we have to find some application so we can publish this. So what we did, but there is a difficulty here, and that is we have to pick that threshold parameter. That's always the problem with smoothing, is you have to decide how smooth. So we thought, well, you know, the usual trick. I mean, I only have like 3 tricks. So one is cross-validation. I couldn't see at first how to use bootstrapping, so I thought I'll try cross-validation, but I can't throw anybody out because everybody is a parameter, right? There are no parameters, they're just the pairwise people. If you throw a person out, you can't find out anything about them. So I thought, well, we can't throw anybody out, but boy, we have a lot of SNP information. We have way more SNPs than we need. So why don't we think about doing something that my student calls CROSS-VALIDATIONESQUE. And it's like cross-validation, although instead of throwing out people, we're going to throw out SNPs. So we pick some of the chromosomes for training and some for testing, and then we use the ones for training. We get our matrix A, and then we start smoothing. A's the correlation. We start smoothing it using different thresholds. We get a whole family of smoothed A's on half of the chromosomes. Then we've got all the other half of the chromosomes. Now I thought, well, I have to use a trick, so I used subsampling. So I subsample again and again a handful of SNPs. And with each handful, I estimate how related they are. So I get an estimate of how related they are, and then I do like cross-validation. I look at how far is my estimate from my smooth, and then I choose lambda by minimizing that. And that works pretty good, and it seemed like a kind of a new version of cross-validation where you're subsampling on the input information rather than on the people. So you've used different SNPs again and again to see how far your data is from your smooth thing, and then picking the minimum. Okay, now we want to try this in an actual application. So something where people are, since Fisher, people have been arguing about nature versus nurture. Like you see, there must be, I wrote one of them, so there must be 500 papers about heritability of IQ, for instance. I'm not going to talk about that today, and recently it was all over the newspaper about heritability of autism. It's something that interests humans. How heritable are things? How much nature, that's the genetic variance. How much nurture, that's the environmental. And the way this has been done for, like 100 years, it's all based on how correlated are the people. Usually, though, usually people estimate heritability using close relatives, twins, siblings, at worst, uncle, nephew, not any more unrelated than that. But kind of a crazy paper came out, and by Yang et al. In Nature Genetics, and they looked and they said, well, let's just throw a bunch of people into the hopper and see how related, see if we can estimate heritability that way. And so they have height is not, the heritability of height is known to be 80%. I heard Carl talking about it when right before the lecture about his son and how tall he would be. And it's pretty well known that it'll be largely determined by the parents, 80%. So and that comes from using these models that I'll explain in a minute. But even in this huge study called GIANT, when they had 180,000 subjects, they've only found 10% of the variance, maybe more by now, but at that time, only 10% of that variability has been discovered. So they wrote a very controversial and exciting paper talking about where that 70% was. And so I want to talk about how they came to that conclusion, how it might be right and it might not be right. And so I'll get back to this. So what this all comes from is this very simple random effects model that, you might have seen this in a lecture in 1940s. So you've got, say, here's height, and it's determined by genes and, environment and random things. And so, and you don't have to have measured those genes. In fact, nobody could. They don't know which ones cause it. But all they do is they say, well, what's the variance? I have a vector of people. What's the variance of it? Well, the covariance of those genes, whether you measure them or not, is the same A that I've been talking about all during my lecture. So if I know what that A is, then I can estimate heritability. And so the time-honored way is to take known relationships. So what you put in for A is something you already know. You know that they're first degree, second degree, you know what that is. And then they just use Rimmel. So they were smoothing. So now, suppose instead you actually knew the genes. So you put in for G the actual genes, and then you could do a random effects model, and now A would be written this way, Z prime M. And you could do this even if the people were unrelated. But the problem is you don't know which genes. So what Yang et al. Did was they said, well, we don't know what the genes are, but we have this 500,000 SNPs, so let's stuff them in there. And so they stuck all the SNPs in there, so Z comes from the observed SNPs, and you get, and this really, Z prime Z is really an estimate for A, but they believe that this will give an estimate that's like this one in that they assumed the people were unrelated, and that it would give, that this would be estimating the causality of some of those SNPs. Okay, so, and that seemed pretty reasonable because they went through, now what kind of data did they have? They had a population sample, and most of you don't do that kind of stuff, but those are like all the people that are in the study. Maybe some are collected in Baltimore, some in Cleveland, but there's no reason that there would be relatives in there. They only get there by chance. They've avoided relatives. Then they go through and they prune out any relatives that they can find. So they throw out as many relatives as they can by looking at how correlated they are. So they have an essentially unrelated sample. And so from that, when they get a heritability, then they're making a causal inference that heritability is caused by some of those Z's, which is kind of interesting because we can use our same technique, however A comes, we can smooth it, right? So we get this Z prime M, and it's a noisy estimate of how correlated the people are, so why don't we try smoothing it and see what happens? If you don't smooth it at all, that's what they're doing, and if you smooth it, that's TREELET. So let's see what happens in real data, and I'm going to skip the simulation in the interest of us being behind. And I was more interested in body mass index because everybody knows everything about height. So body mass index is believed to be 50% heritable. And that's based on studies of close relatives. But those studies always make some very strong assumptions about correlation between environments. And obviously people who grow up in the same household have the same food and so forth. So there's a lot of correlations, and there's correlations between genes and environment. Well, at least if we use a population-based sample, then the environments really will be, I'm pretty sure that my third cousin isn't influenced by what kind of food and exercise I have at my house. So I think that these are basically going to give us more reliable estimates of this, but they're going to be gotten in a strange way in the sense that I'm not going to have any relatives. I'm only going to have distant relatives. And so what I found, you can apply, get these data off the web. There's this sample of people who are of European ancestry, and they have their body masses, and we adjust them for a few covariates. And the maximum relatedness is third cousins, and basically there are no large clusters of relatives, and most of the people are basically unrelated altogether. So we get A, and A has a lot of, it's almost all nearly zero. We apply these smoothers to it, and this is what happens. So we start off down here, and on this end is the naive estimate. On this end, no smoothing, and we get that the heritability of body mass index is about 11% or 12%. But then once we start smoothing, this line says, as I smooth more, my heritability goes up, up, and then it plateaus. And then I can, because this is a random effects model, I can do a likelihood. So this line is the likelihood, the profile likelihood, and it's crashing. I mean, this is the minus the log likelihood. So log likelihood is climbing, really. And down here, just when this is at its maximum, this happens to be at its minimum. So that is the smoothing that we would pick. And then it's really remarkable because we find that body mass index is heritable at about 50%, which is just what other people had estimated. And we thought that was pretty amazing that you could get that from unrelated people. Now the question is, so it went from this amount to that amount. So it seems that we've answered one question, which, because I don't think there's anything wrong with smoothing it, that's probably pretty close to the truth about body mass, and it's not confounded by environment. But then the question might be, well, who's right about, does this say anything about the missing heritability, though? I mean, we found all the heritability, and we used just some of the SNPs. We used 9,000 of them. So does that mean any of the things that they said about, height, about the missing heritability? Do we learn anything about that? We certainly learn that smoothing helps us to recover heritability, but what does it mean? So in a very nice paper by the same authors, but including Eleanor, they looked at that data more carefully. They really cleaned out the relatives, and they looked at a much bigger sample of body mass index. And they did some interesting experiments by looking chromosome by chromosome and in genes and out of genes, and they came up with 17% of the 50% was actually due to small genetic effects that were tagged by the genome. So is it the case that this is the between 17% up to 49%, is that missing heritability that people are going to find some other place, like in rare variants, or is it not? And unfortunately, statisticians can't answer that because we know very well that correlation does not imply causality. So we can't figure it out, but we've at least found that we can estimate heritability a lot better if we smooth the matrix. And also we've learned something about how well smoothing works in really sparse information. So what we want to do next is try these ideas out on a phenotype of greater interest, like autism, where people are really worried about environment and how much it affects things. So I haven't got my 5-minute flag, but I'm sure no one will complain if I finish early. So let me summarize. High-dimensional inference works better if you do some shrinkage. I think Stein said that first, and I'll say it the last time as of this minute. And that modern techniques like TREELETs really facilitate smoothing, that we've come a long way in terms of how we smooth. We don't just shrink to zero, but there's still some magic in smoothing. And that traditional dimension reduction like PCA are great for global smoothing, and these more facile things like TREELETs are great for more complex local structure. And then on the practical side, we were able to estimate very distant relationships better by using the whole matrix, and that hopefully will help us find genes for schizophrenia, which is what the PLOW project is about. And And so then, still I think there's many, many, many large-scale inference problems left, but it's nice to see that the concepts introduced by Brad Efron in his early career are still very relevant. So thank you.